to the next speaker. The next speaker is Biman Sarkar. The title of his talk is The Impact of Flexible Bed on the Interaction between Obliques and Multiple Surface Piercing Porous Barrier. Biman Sarkar.
Hello, I am audible. Hello.
Yes.
Hello.
Yes,
Okay.
Biman. You can start sharing your screen and speak.
1 minute,
Start
sir.
presenting.
Is it visible?
No, still it is not yet visible. Yes. Hello, you start talking. I think you are mute or not audible, Biman sir.
Hello. I am audible. My screen is visible, sir.
Yes.
Okay. Good afternoon, everyone. Myself, Biman Sarkar. First of all, I would like to thank the organizer, Professor Michael Milan and Dr. Susham Boral, for giving me such opportunity to present a paper in the International Workshop of the Ice and Ice Sheet 2023. I would like to also thank Professor Sahu sir. Introducing myself, I am Biman Sarkar, a PhD scholar in the Department of Applied Mathematics, University of Calcutta. My supervisor is Dr. Shomen De, Assistant Professor in the Department of Applied Mathematics, University of Calcutta. Today, I am going to present a paper entitled The Impact of a Flexible Bed on the Interaction Between Oblique Waves and Multiple Surface Piercing Porous Barrier. First, introduction. In the context of wave interaction with floating ice or elastic plate, the study of coupled flexural gravity waves are a point of contention among the researchers and engineers due to the increase in scientific activities in Arctic and Antarctic ocean areas. Fox and Square, 1990, discussed the first evaluated solution of the Greenhill's 1887 mathematical models for the sake of geophysical interest. Das and Mohapatra, 2019, modeled a radiation problem involving submerged sphere where the upper surface was covered by ice plate and the lower surface enveloped by a flexible base surface. Also, the analysis of wave interaction problems with flexible seabed are most relevant issue among the scientists and engineers in contrast with the past. Chiba et al. 2002 studied a linear hydroelastic free vibration of a cylindrical container with rigid sidewall and flexible bottom, along with the consequence of liquid-free surface tension. Mohapatra 2017 investigated the radiation problem for the first time by a submerged structure like rigid sphere in an ocean of finite depth with an elastic bottom surface by employing the multiple technique. Our problem is, here the problem sketch, we consider the four partially immersed thin porous barrier which are situated at the position x equals to b1, x equals to b2, x equals to b3, and b4. The fluid is of uniform depth h, and at the bottom we consider thin elastic plate, which is our flexible base surface. And for this various configuration, the whole fluid region divided into 5 region: R1, R2, R3, R4, and R5. One can also find such type of construction for ice cover, thin elastic plate at the free surface and the barriers at the bottom. One can also find such type of problem. Now here in this problem, we have the velocity potential phi, which satisfies the modified Helmholtz equation in each subdomain as given in equation number 1, along with some boundary condition. First of all, free surface boundary condition is given in equation number 2, and the bottom condition, which is very important for our problem, bottom condition on the flexible bottom surface is given in equation number 3. Here D is the given the expression d1 by rho fg, where rho f the fluid density, d1 is the flexural rigidity, d1 is depend upon the Young's modulus and Poisson ratio nu, and delta is the thickness of the flexible bed. Okay. In equation 4, we have it is the boundary condition along the porous barrier, which is given in equation number 4, where Gj is the complex porous effect parameter. The real part of porous effect parameter denotes the resistance effect of the porous material along against the ocean flow, where the imaginary part signifies the inertial effect of the fluid inside the porous material. Here we also considered the porosity as non-uniform. Consider the porosity is non-uniform, which is function of y. That is the depth. It is on varies the depth of the fluid along y direction, and it is given in the expression gjy, which is 4y lambda. Lambda j is a constant, and bj's are the barrier separations. Here, another condition is the edge condition at the corner of the thin porous barrier, which is given in equation number 5. And the eigenfunctions psi and y are given in equation number 6. These eigenfunctions are not in general orthogonal, but it also satisfies the mode coupling relation, which is given in equation number 7. The dispersion relation for this type of problem is given in equation number 9. There are the equation has 2 positive non-zero real roots corresponding to traveling waves, 4 complex roots occurring as plus minus, and a conjugate pair satisfying the damped progressive waves, and infinitely many purely imaginary roots associated with the Evanson modes. Now, method of solution. For the geometry of the problem, for 5 different regions, we have 5 different velocity potential for each subdomain, where the Rnj and Tnj are unknown constants, and R and T denotes reflection and transmission coefficients. That reflection and transmission coefficient has to be quantified in the next sections. Now, we introduce 2 functions. First, we introduce horizontal component of velocity, which is given in equation number 11, and potential difference, which is given in equation number 12. And along equation 11 and 12, with the help of the porous condition, as we showed in the previous slide, we get the equation number 13. Next, we consider some constants, some notations in equation number 14, along with a step function chi jy, equation number 15. Next, we use mode coupling relation, equation number 7, on the potential difference qj, along with the condition 13, and this leads a set of integral equations. And these integral equations are converted into a single one, and converted their range into 0 to h by using equation number 14 and 15, so that we get a single integral equation. Single, not, this is actually combined integral equation in equation number 16, where the kernels are given in equation number 17. Now, for transforming this integral system of equation into a matrix form, we introduce a transformation formula given in equation number 18, so that the above system of integral equation transform into a matrix form as given in equation number 19. Now we again use equation number 14 and 18 so that the matrix equation has a simplified form as given in equation number 22. You can see the equation 22, which is V equals to W into U. If we find W, because U is given in equation number 14. If we find W, which is given equation number here 23, then we can find V, and if we find V, you can see V has the component along with reflection R and transmission T, so that we can find the reflection coefficient and transmission coefficient. So our target is to find the matrix W. Okay. Now we introduce multi-term Galerkin approximation technique. Here we consider n plus one term Galerkin approximation, which is given in equation number 24. In this section, we have to choose some basis function, which is given in equation number 25 along with 26, where u2 and x are the Chebyshev polynomial of order 25. Actually, at the sharp edge of the thin barrier, there are half singularity, which I have mentioned in equation H condition, that this is the singularity. You can see Qj is order of Lj minus 1 of order half, where y tends to Lj minus 0. So the half, we have to tackle such kind of singularity by choosing suitable basis function here. So we here choose the Chebyshev's polynomial so that we can tackle such kind of half singularity and get the exact and highly accurate values of reflection and transmission coefficients. Now, equation 19 is used to use into the following system of integral equations, and with the help of 24, we get equation number 27. So that now we have some formulation and some mathematics, so that we can transfer the equation 27 into a system of linear equation 28, where the components are given in equation number 29. Now the expression of the kernels NJL we use in 29, so that the components can be represented in terms of modified basis functions given in equation number 30. Now, taking the matrix P as 4 by 4 matrix, equation 24 and 30b successively used in 21, so that Pj are evaluated as in equation number 31. Now we also here formulated hydrodynamic wave force and dissipated wave energy. According to linear Bernoulli's equation, the dynamic pressure jump over each porous barrier is given in equation number 32. If one can integrate along such pressure jump along the barrier, then one can find the horizontal wave force. And after dimensionless that wave force, we get the dimensionless horizontal wave force expression is given in equation number 33. The reflection and transmission coefficient satisfies the energy balance relation in equation number 34. This relation can be derived by using Green's integral formula. Here Ke denotes the amount of wave energy dissipation. One can study for rigid barrier, then that Ke is exactly equals to 0, so that the mod R square plus mod T square is exactly equals to 1. But however, we are studying here for porous barrier, so that Ke is in general not equals to 0, so that our energy identity always less than 1. Analysis and discussions. Here we consider for numerical analysis some fixed values of some parameters, and we also choose only 3 terms, that is n equals to 2, for getting highly accurate values of reflection and transmission coefficients, because Galerkin approximation is one of the highly converging method for finding the solution of integral equations. Here are some validation for our results. Table 1 and table 2 shows the validations. In figure 2, we considered 3 porous effect parameters values. As you can see that amount of porosity increases, amount of porosity means magnitude of amount of porosity increases, mod R decreases, and wave force is also decreases. And lambda is a constant which is inversely proportional to the porous effect parameter. You can see that if values of lambda increases, reflection increases and energy dissipation decreases. In this figure 4, we have considered 3 different thickness of the bottom surface, so that the thickness increases, reflection decreases, and also amount of energy dissipation decreases. And for wave energy, for wave force and transmission, the reverse characteristic is occur in figure 4b and 4d. In figure 6, we actually consider 4 type of configurations. Here, single barrier, 2 barrier, 3 barrier, and 4 barriers results are compared. For you can see for amount number of barrier, where the number of barrier increases, amount of wave energy dissipation also increases and transmission decreases. And for reflection and wave force, the oscillatory nature increases when the number of barrier increases, because number of barrier increases, then multiple interaction occurs, so that the number of oscillations also increases. This is an important result. Here we compare our result for flexible bed with the result for rigid bed. You can see that for our flexible bed, the reflection and wave force becomes more oscillatory for flexible bed compared to rigid bed, and the energy dissipation increases for flexible bed compared to rigid bed, and transmission decreases for our flexible bed compared to rigid bed. Here is some validation of our result with the results of Liu and Zhong. Conclusions. The study reveals that the porous effect parameter, especially non-uniform permeability, helps to reduce wave energy and protect the offshore structure from incoming wave attacks. The main key structure of this model is to establish the usefulness of the flexible base in the classical problem of water wave scattering by multiple barriers. For this purpose, we analyze a comparative study along flexible and rigid bottom. From the graphical representation, it is actually ensures that better breakwater construction flexible base rather than rigid bottom. It is inferred from graphical depictions that as the thickness of flexible bottom increases, both mod R and Ke decreases, but mod T and Kf increases. This research discloses the fact that the change in number of barriers makes the reflection more oscillatory. Furthermore, mod T and Kf behave contrasting nature vary by varying the number of barriers, and peaks of Kf reduces as the number of barrier decreases. Also, mod R Kf epsilon and Kf tends to 0, whereas mod T approaches to unity when incident angle gradually goes to 90 degree. These are the references. Thank you.
Thank you, Biman. You have nice presentation. Any question from the floor? If not, I will have few questions. You have taken.
Maybe I can ask a question.
Yes, please.
Sorry to
Yes.
jump in. Yeah, I can ask a question first of all.
Sure, sure.
Have you thought about changing the grading these barriers in some way so that you get there's this changing the size of them in a uniform way to attenuate or anything like that?
Sir, you are for the flexible base.
I've seen some interesting papers where they have this like graded arrays.
I'm not understanding, sir. You are for the flexible base thickness.
Just changing them, changing it in a way that grading it to try and just gently absorb the energy.
Change in energy.
Yeah, maybe I ask another question, but do you think you could extend your results to 3 dimensions?
3 dimension, actually, we consider the cross-sectional view. I can show you the picture. Here. Cross-sectional view. Here the XZ plane is the free surface, and the bottom vertical direction is the y-axis.
Yeah, but could you make it 3-dimensional? Could you have a finite plate, you think, or?
Here also we consider 3-dimensional, sir. You can see the potential function are phi j xy along with e to the power I mu z minus I omega t.
But don't you then factor the y out in some way, right? Do those plates go to infinity, or are they finite?
Okay, sir.
Are the plates infinite or are they finite? Maybe I missed something.
The fluid domain. Fluid domain.
No, yeah. Are the plates finite or do they go to infinity?
The plate.
Plate is infinity, sir. Plate is infinity.
Yeah. All right. Thank you.
Okay.
Thank you,
Even you have taken the porous effect parameter as a function of y. Am I correct?
Yes, sir. Yes, sir.
Is this the first time you are using this as a function of y, or it is there in the literature?
Literature, sir. It is in the literature. It is actually this paper is also published, and previously we considered that type of porous effect parameter from Gain and Gupta's paper, and
No, in that case, the
they
Darcy's law. I am a little confused about the Darcy's law, how it is taken care of. Anyway, this is one question. I have another your energy balance relation. If you go back,
energy balance relation.
yeah.
At once, this is
Here. You are looking at a flexible bed, but this energy balance relation is independent of the bed topography or what? Because this talks about the porosity structure, the K epsilon term, but it does not talk about the flexibility of the bed.
Flexibility of
Bed flexibility,
sir,
it is not, there is no contribution from bed flexibility to the energy balance relation.
Actually, we take the contour integration using Green's integral theorem.
No, still
So
your bed contribution should come because bed is a flexible bed, and you have a fourth order term. That D term is there. That contribution is not coming here.
Yes, sir.
So that contribution should come. I guess that contribution should come in associated with the T parameter amplitude of.
It mightn't absorb energy though, right?
Yeah, because it's a flexible bed. The energy contribution should come in the bed flexibility should come in the equation 34 should be modified.
But maybe the
that-
bed, even if it flexes, it mightn't absorb energy. I don't
Yes.
understand how this G is a function of Y. But
That
I'll
is a
leave
very
that.
good
All right.
question. And
If there's time, how do you account for the G as a function of Y when you've got this, when you do the eigenfunctions?
Sir, we have in the
Being-
previous literature that G is a function of Y, which is the vertical depth. It may be taken as I or Y square or polynomial of Y. We take here the simplest form. And
so Y is the vertical, Y is down, is that right?
vertical depth.
Okay, and Z is flat.
Z is flat.
Okay, yeah, that makes sense. Sorry. All right.
okay. And but most of your calculation you have done with taking the porous effect parameter as a constant. You have not taken G as a function of Y. Am I correct?
Sir, we have considered here the values of lambda 1 by h.
No, I'm
lambda 2
talking
by
about
h.
your GY.
GY is, sir,
everywhere is
variable.
taken as a constant.
Here constant value is considered, but in this figure 3, we consider the variable porosity.
No, variable means in the it is not a
Haven't
function of
you-
Y.
Variable means G is a function of Y multiplied by a constant lambda
Okay,
and
okay,
varying.
fine. Okay, I have.
But even that,
Really?
it's one more question.
Yeah,
If
please.
I can ask it. That energy balance that you wrote down, where you take the real part of G, has that kind of energy balance appeared before? I feel like somehow that has that appeared before, or is that something that you think is new?
4 means in the
No,
porous
that
effect
equation with the energy, the one you had before, the energy balance equation. Yeah.
One minute. One minute.
You wrote down an energy balance equation. We just saw it before. It was the slide that Professor Sahu was asking about.
Yeah,
This
I
one
think-
here, yes. Is that new? Has that appeared in the literature before for other barriers?
4 means a number
this
of barriers.
I'm just wondering if,
Consider
but I'm
4
asking
barriers.
that, yeah, the fact that, and if there were 6 barriers, it'd be the sum from 6. There's nothing surprising about that. But
Okay.
I'm asking if, just take that formula, that type of formula, has that appeared in the literature before? Or do you think that's new? Because I've never seen it. I mean, did you find that in another paper and you got one similar, or did you just find that from scratch, from you?
Okay, sir, I will surely our next.
I'm asking,
paper.
I'm asking, did you copy this from someone else?
No, sir,
Maybe
I am
I'm right.
deriving. No, sir, I am deriving mathematically by using Green's integral formula and get this
But
expression.
did you, yeah, I understand that, but did you, you're not the first person to use Green's integral formula. Are you the first person to get a result like that? It's a hard question. I mean, did you, I'm just wanting to know how new it is, because it looks new to me. I'll ask the question in the chat. Okay, I'll write it in the chat.
In fact, apart from that, as I told, that role of the bottom flexibility is not included. So this appears to be because you are taking a flexible bed, so the bed effect should come in.
If you look in the chat, I've written the question. I'll read it out to you.
Okay.
Okay, it'll help you with my accent. Is this formula new, or did you copy from a similar derivation?
Sir, this formula is similar type, but exactly new, not this is, but we formulated for our problem. This is new, but in previous problem, there are some different models, and the technique is same, but they derive the energy dissipation. We just followed that technique and derive for our model.
Yeah.
Okay, thank you. I think we'll stop here. We'll go to the next speaker. So, Biman, can you stop sharing?